Well, hello everybody, and welcome to the second of today's sessions from Smart Vision. We're looking again at healthcare, but this time we're looking at regression techniques for healthcare applications. My name's Jarlath Quinn. I'm joined online today by my colleague Rachel, who'll be making sure everybody's logged in correctly. Again, if you have attended these before, then I apologize for the next few slides, but if you haven't attended them, then the next few slides are relevant for you because you should be aware that if you haven't attended any of our sessions, that our sessions are recorded. So you'll be able to listen to them again afterwards. There is some slideware here that we'll be using. There'll be a lot of live demonstration, but we'll email a link out to you after the session's ended so you can download those, copy of the slides after the session's ended. And if you think the session's particularly relevant for colleagues who are unable to attend, it may be possible for us to arrange a rerun of that if we can get enough of them together. The best thing to do is simply to send us an email or give us a call, and we'll see if we can arrange that. Now, with regard to asking questions, all the lines are muted. So we ask you to use the chat panel. Try and keep an eye on that, but if we run out of time, we'll follow up with you offline as we do normally. If you don't know who we are a partner organization to IBM, and we specialize in statistics and data science and analytics and AI and all that type of stuff. And we're a gold accredited partner to IBM as well as a company called Predictive Solutions Data Robot. We work with open source technologies as well, not just off the shelf technology, but R and Python and all those other types of open source languages. And we're made up of a veteran team of individuals who all have decades of experience working in the analytical technology industry, such companies like SAS and SPSS and IBM. That means we've got a lot of experience of applying statistical and data science, machine learning techniques across many different sectors, healthcare being one of the ones that we've worked in many occasions in the past. This particular topic is about regression, which is of course used across all different sectors, but we thought that trying to cram it into some of the other sessions here wouldn't really work. We need to kind of devote a bit of time specifically to it, particularly for techniques like linear regression and logistic regression, where people are new to that. It's useful to have a proper amount of time to explain and really lay the foundations of how these techniques work and how they're applied. So our agenda today is we're going to be exploring relationships between scale variables and correlation. Some of you may have seen this in the previous session. If you've seen it beforehand, I apologize. We are going to go over it slightly again somewhat. Then we're going to introduce the basics, the basis of simple linear regression, for moving on to multiple linear regression, identifying problems in linear regression models, keeping an eye out for that, for looking at logistic regression and working with logistic regression to model an application where we're trying to predict low birth weight. So the first thing is that regression, when people say I used regression, they usually mean linear regression. But in fact, the term itself just refers to a family of different techniques that are used predictively to model and predict outcomes and generate estimates for thousands and thousands of different applications. Linear regression is used when the outcome is usually continuous in nature and where the relationship between the fields can be described using straight lines. Logistic regression is used when the outcome consists of a category, so a success failure outcome or a yes no outcome. So you can use it with more than two categories. You can use it more than dichotomous categories. You can use it with three or four categories. That's called multinomial logistic regression. This is a little bit more complex, produces more output, but it's certainly an acceptable technique that's used. Then you get things like quadratic regression. These are non-linear regressions. The variant linear regression when the outcome is continuous, but the relationship between the dependent variable and the predictor variables, the things that you're trying to use to predict the outcome or model against, is actually curvilinear in nature, and you want to preserve that curvilinearness. So it's a slightly more complex form of regression. Again, we have videos on this that look in these in more detail. And one of the videos I did recently was on Poisson regression. Poisson regression is is these are continuous variables as a dependent, but unlike linear regression, they're kind of spread. It's more about the situation, which is different. Poisson regression is used when modeling count data, which is particularly relevant for healthcare settings because they're used a lot for never events. So things which really don't occur that often, but maybe get one, two, three, four of them, over the course of a period of time. So it's used a lot, for example, in insurance, where you're trying to model how many claims somebody or a business might make over the course of over the course of a lifetime of a policy. But it could also be used for visits. So it's used a lot for visits. So visits to A&E or visits to wards, where you get, values of one, two, three, four, and it has a particular type of distribution. So if that sounds like the sort of thing that might be of use to you, the best thing to do is just check out some of our other videos. I've done one specifically on Poisson regression. It'll show you how to run that. But if you haven't done linear regression before and you're completely new to it, then this is a good grounding because all of these techniques, I would say that the foundation of them, the fundamental concept behind them is linear regression. Linear regression is very much the sort of grandfather of all statistical techniques. In healthcare, it's used to model the relationship between things like blood pressure and diet, salt intake, let's say, estimating treatment costs based on comorbidity, predicting visual acuity based on treatment and age-related factors. It could be estimating PSA count based on age and things like ethnicity. Estimating calcium levels based upon vitamin D levels and age and sex. And predicting recovery time based on demographic or factors or the severity of an illness or an injury and treatment factors, the types of treatments, a regime that's been used there. So lots of examples where we might have a continuous outcome, which are dependent or related to a number of other factors, and we want to see the effect of these factors on that outcome, and we might even also want to see if we could predict the outcome on the basis of those factors. So regression is a term that is shortened from the term regression to the mean. So it's actually short for regression to the mean. And it simply means falling back towards an average that, there is a kind of underlying average relationship. That's what the mean is that it's talking about, the sort of averaged relationship between two factors. If you, for example, were to look at in this screenshot here, percent reliant on public health care and percent unemployed, each of these points is a US county. These are US counties, so it's saying basically it's a positive linear relationship. It's simply saying that, um, as uh, as unemployment is higher in certain counties, you tend to find that the proportion of people who are reliant on public health care and don't have private health care, it increases as well. So of course, they're both measuring a socioeconomic underlying socioeconomic factors, so as we would expect. So it's not a terribly surprising relationship here, but we could actually average one of them. If I took the average, the mean percent reliant on public healthcare as opposed to the individual value, just the mean, you can see that this value here, this relationship starts to become much more linear. So hence regression to the mean. I mean, obviously, what's interesting is, and this is important, is that, when you get into the extremes of distribution, you often find that the relationship kind of starts to break down. I mean, you can imagine a straight line going through this scatter plot here, and that straight line would represent the overall average of the relationship between the two factors. Again, regression to the mean, the average. So this is what that straight line would look like. Obviously, most tools, like SPSS and other tools, will calculate these averages for you. And the regression line is drawn in such a way that it minimizes the differences between the points in the line itself. So you look at this line here, it's put through there because it's basically trying to minimize the distances between the points in the line. And if you were to do that, you would end up with this line called the line of least squares. The reason why it's called the least squares is because, as you can see, that the deviations or what's called the deviations between the individual counties and the overall average. Some of them are positive, some of them are above average, some of them are below average. And if we were to add them all up in such a way that we were trying to, draw a line that minimized the difference between, if we add them all up, the positives and the negatives would cancel each other out. So that they just end up with zero. So the convention is that you square the differences. So a difference of 2 becomes 4, and a difference of -3 becomes 9 because you're squaring the -3 is 9. And what you do is you add up all those values, and the smallest number you can get to is related directly to the line that fits the best through it, the line of least squares the average. And that's what a linear regression line looks like. So the thing you have to bear in mind is that these relationships are under no obligation whatsoever to fall along that line. And the line is being a straight line is under no obligation to follow the pattern that it sees within the data because it's straight. It can't, it's unbending. So you'll get situations that this line where this line goes straight through a relationship, even though that relationship is curvilinear, or where it puts straight through a relationship and where you've got an extreme value because you're trying to minimize the difference. It is an average after all. The line itself is dragged up or is influenced by this extreme. It's just the same as in the same way if you were to calculate average height or something for a group of people in the room and somebody walked in who was 8 feet tall, the average height would probably increase based on that. Obviously, the number of cases you have means that extreme values can have a greater effect upon the regression line. Uh, 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 if you have a very small sample size, extreme cases have a greater effect than if you have a very large sample size. But you can also get, this regression line where you've just got two values. Here we've got the two values. We've got a value of 8 and a value of 19, that looks like, maybe 19. Two values, that's it. It'll still draw a straight line between it. So the point is, visualize the data and be aware that this line is just an average, after all, of all the concomitant problems that averages entail. Okay, so measuring linear relationships correlations. We talked about this in the last session where we looked at examples of little scatter plots here, and I pointed out that these scatter plots are all points. These are all automobiles, each of these vehicles and automobiles. You can see there's some extremes here. We've got an automobile here which doesn't really fall within the same relationship as all the other ones, but we can come up with values which measure the strength of the linear relationship called correlation values. If we look at, for example, horsepower against vehicle weight here, we get quite a strong positive correlation, positive number, 0.859. If it was a perfect relationship, that number would be equal to 1. It'd be a perfect relationship. And if it was a random relationship, it was just a random cloud, that value would be equal to 0. But it's closer to 1 than it is to 0, so it's a strong linear relationship. This one here is less strong, still a positive linear relationship, still a positive correlation value, 0.43. And it's simply saying here we have the relationship between miles per gallon of each of these vehicles and the time to accelerate from 0 to 60. And it's simply saying that, generally speaking, if you put a line through this, it's saying that generally speaking, if your car does better MPG, it probably takes longer to accelerate from 0 to 60. That's partly because there's probably smaller cars, more fuel efficient. And you can get negative relationships. You can get time to accelerate from 0 to 60 against horsepower. So this could be like, reflex reaction time against alcohol consumption or something like that. You do expect one to have a negative effect on the other. So anything has a negative effect on that, and you get a value which is closer to -1 because linear correlation values are symmetrical. They go from -1 to +1, 0 in the middle. And indeed, if we looked at a completely random relationship here, this is miles per gallon against mileage. The two values are not related to each other. The age of the car is not related to the miles per gallon. It's going to get very close to 0. And that's reflective of the fact that it's a non-linear random relationship. But bear in mind, as I say, you can get curvy linear relationships, which nevertheless, the straight line will go through ignoring the curve itself, this hook-shaped relationship, and it will still give you a correlation value off the back of that. Um, so bear in mind that it can only see linear relationships. It can't. It just ignores or bulldozes its way through non-linear relationships. And as a result of that, statisticians try different things. They might try a non-linear technique, or they might try and straighten the relationship. One of the ways in which they sometimes do that is by taking the square of values or the log of values, and that helps straighten a relationship out for a predictor varied field. You can see here that I've created this variable miles per gallon squared. I've literally squared it in order to create this chart. And if I took the square root of that value there and calculated that and changed this value, you'd find that it would straighten out that relationship. So the next thing is that you can actually see correlations as percentages. So these are Pearson's correlations. So if you got a correlation here, for example, of 0.859 and you square it, you simply multiply it by itself, comes out as 0.738. That means 73.8%. This is called the R square value because the correlation is called the R value, and this is called the R square value. And that R square value is the key measure that is used to assess whether the level of fit in a linear regression. So you're usually trying to get the highest R square value you can, because that R square value reflects the percentage of variation in one variable that can be explained by the other. So it's almost like a Venn diagram. If you had an R square value of 0.5, you'd imagine two circles where half of the area in both circles overlapped with the other half. It means that 50% of the variation in one factor can be explained by the other factor. And that would obviously be a fairly strongly related value. And indeed, to get an R square of 50, that would be a correlation of 0.7, which would be a strong correlation. 0.7 squared, of course, is 0.49, very close to 50, so just over 0.7. Okay, how can we express these linear relationships as predictive models, however? We can measure them. We can say, oh, look, that's the strength of the relationship, but how can we express them? Well, um, the simple answer is to ask, how long does it take to cook a chicken? That's one of the simplest ways to think of it. It turns out that there are little formula out there that help you know how long it takes to cook a chicken. If you're Julia Childs, it's 7 minutes per pound plus 45 minutes, and if you're Delia Smith, it's 20 minutes per pound plus 20 minutes. And these are under certain conditions. I don't know what gas mark or temperature. But this equation that they're giving you, this sort of rule of thumb, is in fact the equation for a straight line. It might not seem that way, but that equation for a straight line is exactly the same as the equation for linear regression. So when you run a linear regression, it gives you these two values. It gives you the x per, which is called the coefficient, plus some number that you're adding on at the end. That's the constant. And depending on whether or not you're a mathematician or a statistician, you might show this as y equals mx plus c or y equals a plus bx. It's the same equation, where the x is the observation. That's the pound, the weight of the chicken, where we're trying to predict the time, which is y, and the 7 minutes per pound, that would be 7 here, coefficient of that, plus c, which would be plus 45. So that'd be y equals 7x plus 45 in that example there. So when we run our linear regression, this is what we're going to see out the back of it. And indeed, you can ask SPSS, it will actually, when it does a scatter plot and you put the line least squares through it, it will actually give you the equation itself. So it says, look, if you want to predict percent reliant in healthcare, then what you do is you'd multiply percent unemployed by 1.16, so it's plus adding on 10 at the end. That's the constant in the end. And that basically is the equation for that line. And that line, as you know, is basically an average. It is the line of least squares. So the line of least squares is then turned into a formula, which becomes a predictive model. Okay. So when we run the linear regression, we're going to see these elements. We're going to see these things coming out of, it's going to find the equation for the line of least squares. And it's going to tell us how strong the relationship is using an R square value. Let's look at our first example here. We're going to use linear regression to model regional per capita cancer mortality rates. And I'm going to jump out to the data set. Let's see, how many cases have we got here? We've got over 3,000, about 3,047 cases. We've got a target field here, which is death rate. And I'm just going to do some correlations first of all. Let's just have a look at some correlations. So just do simple correlations here down to bivariate. We'll pick a couple of them. Here's mean per capita cancer mortalities. And I'll look at things like median income. And I'll look at, let's see, percentage with where the highest education achieved is.
Lola.
Yes?
Yeah, I'm still seeing the slides here.
Right. Okay. That's because it's not sharing. It's lost to share again. Okay. Okay. Thank you for letting me know. Let me then share screen. Okay. There we go.
There we go. Yeah.
Okay. So we have this data set here. It's got 4,000 records in it. Sorry, 3,047 records in it. We've got various measures which you can use. Actually, there's quite a lot of measures in here. Um, One of the tricks you can do in SPSS is if you want to mask out fields that you're not working with, you can actually go to utilities and you click on use variable sets. You can tell it to use a subset of the data. You can define your variable sets on the utilities. And I'm going to say, just show me new variables and the ones that I've reserved for regression analysis. So I click OK at that point. It just gets rid of some of them, masks them out, makes it simpler. And if I go down to correlate again, analyze, correlate bivariate. See, I've got a smaller number now. I'm just going to look at median income per county against, let's see, population and poverty. And let's see, population government health coverage. Let's see, what percentage of county with government provided health coverage. Okay. And we click OK at that point. I'm actually going to ask it to switch off the lower triangle, switch off, show only the lower triangle of the matrix and to switch off the diagonal. Click OK at that point. And it gives me three correlations. It looks like there's a lot of data in here. One of these is a significance test, which I'm not really interested in. One is the number of cases, and here are the correlations themselves. I can pivot this and say, go to pivoting trays and say, just show me the correlation values. The correlation values, you can see they're all strong correlations. It's saying basically the higher the population, the higher percent of the population in poverty, of course, the lower the median income. So that's a negative correlation. Whereas here we've got the percentage of county residents with government provided health is also negatively related to the median income. And whereas percentage of county residents with government provided health is positively related to percent of populace in poverty. As we would expect, these two variables would be positively correlated, and that these two variables would be negatively correlated with median income. Okay, our key variable that we're interested in here is this one, which is mean per capita, average per capita per cancer mortalities. So let's look at that. Let's throw that variable in now and double click on it and see which of these variables is strongly related to it. So we'll click on pivoting trays and go to statistics again. Put that into the layer controls. And I'll just make this a little bit wider. So we've got mean per capita cancer mortalities. Well, they're all but minus 0.24. Now that's median income is negatively related to that. Positively related to that is percent in poverty, and positively related to that is percent of county residents with government provided health coverage. If that's the only health coverage they have, then that is positively related. And if the correlation was zero point 0.4 exactly, that would equate to an R square value of 16%, because it'd be 0.16. Because 0.4 squared is 0.16. So it means there's 16%. Now, maybe using combination, maybe doing multiple linear regression would be able to build a predictive model which might estimate the cancer mortalities based on these socio-demographic values more accurately. And to do that, I'm going to go to Analyze, and I go down to Regression, and go to Linear. which is up here at the top. Just hit reset here. This is our dependent. This is our key variable here, mean per capita, cancer mortalities, and mean number of cases of cancer diagnosed annually. Well, we would expect that, wouldn't we? I mean, obviously you've got a lot. Isn't that kind of related to that? It's like, that's the mean per capita. That's the number of cases of cancer diagnosed annually. You kind of expect that to be related to it. So let's try and pick some of these other variables like median income per county. I'll throw that in. And I'll just run with the default settings on that so you get used to the output. So we can work our way through the output. And what you get with regression output is, I'm just going to hide some of the other bits output here, is you always get the same sort of format. What you get is some information here about the variables that have been entered. Well, there's only one variable that's been entered. And the method that's been used is enter. That means forced entry. That means you're forcing it into the model whether or not it helps or not. So it could be random. It could be the percentage of people who are Sagittarians or something like that. It would still force it in. And then you get your model summary table. That's the first thing. The model summary table gives you, well, look, it gives you an R value here, 0.429. Where have we seen that before? Here it is. It's minus 0.429 here. It ignores the direction in regression. It's minus 0.429, but it ignores the direction, but it's the same value. It is actually the correlation value. And as you know, when we square 0.4, we get 16%. Well, this is 0.429, so it's a bit bigger. And when we square that, we get 0.184, which is 18%. The adjusted R square is the value which we normally quote in when we're talking about linear regression. Adjusted R square is an adjustment for the sample size and based on the standard error and stuff like that. It's always slightly lower, just a little bit lower than the R square value. So that's what we're looking at. We're saying that 18% of the variation in per capita cancers, cancer mortalities, can be predicted if you just know the median income of each of the counties, which is each of the records cases in the data set. And the next thing you always get is an ANOVA table. And the ANOVA table here is a significance test. And what that's doing is it's saying, is that better? Is this model better than just simply taking the average? Is it better than just having an average? And we expect it to be statistically significant because the null hypothesis is that it's no better than the average. This model's just going to just point out the average. What is the average? Let's look at the average. If I right click and ask for descriptive statistics, look, the mean is 178. So this is basically saying, okay, well, look, is this model better than just the R square here? Is it better than just guessing that everything's, estimating everything to be 178? Well, yes, it is. It is better because we're rejecting that null hypothesis. And we kind of, if any of these have any sort of predictive power, that's generally always significant. It's always less than 0.05. And then we get to the key part of the output, which is the coefficients table. This is the y equals mx plus c. This is your 20 minutes per pound plus 20 minutes per good measure. And the place where we see those two values are in the B column. That's the coefficients column. And what this says is that you should take every median income per county, and for every value of median income per county, you should multiply it by minus 0.001. And whatever that's equal to, you should then add on 225. And that will give you your prediction, your estimate based upon this variable of the median income of the effective median income per capita median income per county on the cancer rate per capita. Now, at this stage, we can see that they are both of these terms are statistically significant, so they're both helping. And we can also see this value here, a standardized coefficient of minus 0.29. You've seen that before, minus 0.429. That is the same as the R value. And at this point, because we've only got one variable in the model, it's always the same as the R value. In fact, this changes when we add extra variables into the model. And when we add extra variables into the model, it goes from being simple linear regression to a multiple linear regression. But before we get to that stage, let's just look at this coefficient again of median income per county. it's kind of a bit weird because if we double click on it, we can see the actual value itself. The actual value is tiny. It's minus 0.000098. And that's because that number is affected by the units that that variable is measured in. And that variable is measured in, really quite detailed units of right down to individual dollars. So where is it? It's median income there. It's like $61,898. So it's talking about a $1 increase. 68,000, sorry, 61,898 versus 61,899. So I mean, how could we make that a bit more transparent, if you like, in the in the model? Well, one thing you could do is you could turn it into thousands, couldn't you? You could say, okay, I'm gonna actually compute this out. I'm just gonna show you it now. I'm just go med. I'll type med ink. It's a good trick. I'll make it K for 1,000 Ks. Yeah, something like that. And what's that going to be? Median income divided by 1,000. Okay, click that. Click OK. And what do we do? We get this new field at the end here. Look, there it is now. It's 61,690. Now, what happens if I run that? Sorry, I swap that out for my linear regression. I throw that out and swap it around. What's the coefficient? Well, now it's different. See, now it's saying for every $1,000 um, of median income, it's actually got a negative value here of about 0.98. So it's actually taken up you're actually taking away about one per capita, 0.19 for every $1,000 you drop the per capita by, let's say by one. Isn't it interesting? Another thing you can do while we're on that, because of course the units make a difference because we're doing 20 minutes per pound. Another thing you can do is you can go to transform. Here's another trick you can do: visual binning, and I could pick up median income per county and click continue here, and it shows me the whole distribution here. And I'm going to change this to median inc dec this time. That makes it deciles. I'm going to change the labels here to deciles, and I'm going to change it into deciles by going to make cut points here and say, I want you to turn this into deciles with 9 cut points. That means a width of 10%. And look, it'll just slice it in 10%. I say make labels here and then click OK at that point. It says, OK, I'm going to create a new variable for you. Let's look at this new variable. Look, it's grouped. It's created a grouped variable. And if we right click on it and say descriptive statistics, look, everything's about 10%. Yeah. So these are the deciles, see the actual deciles. So I could swap that out and say, let's use that instead and put that in. And I can get away with this because they are true deciles. They're not just rating scales like, low, medium, high or something like that, which is kind of arbitrary. It's not a real number. These are kind of real numbers because we've sliced it perfectly into tenths. So they have a property called equidistance. And now it's saying for every decile that you move up the income, the median income in a county, you get 4 less deaths per 100,000. And then you add on 202 at the end. So this is just a little exercise to show you that it makes a difference what the units are in, and you should feel free to play around with the units if their values are kind of make it difficult to interpret the linear regression equation that comes out the back of it. So let's stick with that. Oh, by the way, let me have a look at that. Let's look at that again. Let's just look. What's interesting here is that it put the R-square slightly higher, 0.197. It's actually a slightly clearer signal. That's probably because some of the extremes and outliers have kind of been forced into these groups, so it's kind of a cleaner, what we call a cleaner signal, less noisy signal. Whereas here, when I divide it by 1,000, it's pretty much it's exactly the same value as beforehand. It's still all I've done is I've just divided them by 1,000. So I've simplified it somewhat by doing that. Is that a good thing or a bad thing? Well, it depends on the context. Okay, let's add in another field. Let's add in some of these other fields. I'm going to add in things like percent of the populace in poverty. I'm going to say percent of populace, county residents aged 25 and over who had, that's basically the percentage who have graduates. Percentage county residents 25 and over. Education, graduate degree. What's that? Is that graduate degree? What's that? I think it's the same thing. As unemployed, this is government provided health coverage, and this is married, putting that in. I'm just throwing in everything here. And now what I'm going to say is I'm actually going to change it and change it to something called forward. Forward means that I want you to put them in one at a time based upon how strongly they correlate to each other. And then I want to look at see how well how well the model works. So I put all these different fields in. And guess what? I'd only picked three of them because it built three models. It started at an R square of 23%, 0.23, and it went up to nearly 30%. So nearly 30% of the variation in mortality could be explained using just these three variables because it chose the best three variables and then didn't use any which it didn't feel were statistically significantly contributing to it. At each stage, of course, we expect the model to show to be significant. We expect the ANOVA table here, what's called the omnibus test, to be significant. And then we get three sets of model coefficients because it's building the model three times over. It starts off, let me just pick this one here, making this a little bit bigger. It starts off with this one that says, okay, the first one I'm putting in is bachelor's degree. There you go. It says for every percent that you increase the number of bachelor's degree, percentage of graduates basically, percentage, every percent 25-year-olds who are graduates or 25 and over who are graduates, you actually get 2.4 less people who died of cancer mortality. That's significant. Then if you add in percent married households, it says for every percent of married households, you actually get one less person. And then as we add in things like the last one here, which is county residents over 60 who are employed, you get zero point 0.3 less people. Notice that these values are changing. They're not the same values because obviously as we add in other variables, those values have to accommodate those other variables. In the same sense, if you're trying to predict how long it took to cook a chicken and you were basing it just on weight, if you added in something like temperature, the weight value would have to compensate for the fact that, that you've got this other variable in there. So now the coefficients change because we're saying in the presence of these other variables. This is how much that impacts the per capita death rate from cancer. We can see that they're all statistically significant at this stage. And we can also see very importantly here that we have what are called beta coefficients. These are called partial correlations, and they are saying that in the presence of these other variables, this is how strongly correlated they are with the target variable. So this one started out being correlated with a value of 0.483, quite strong, the strongest correlation in the data set. But in the presence of these other variables, it no longer has a unique correlation. It actually shares some of the correlation with these other variables. And so it's a little bit weaker. This one here drops from 0.243 down to minus 0.94. So it's showing you how much unique correlation each one excludes with it. And this is a big problem if you put in variables which are basically measuring the same thing, then that can screw up your coefficients. And we have measures called collinearity statistics. We want the variables to be fairly independent of one another. We want the independent variables to be independent of one another. If you right click on this and say, what's this? This is a statistic used to determine how much of the independent variables are linear related to one another, multicollinear. The proportion of a variable's variance not accounted for by the. It says basically it is calculated as 1 minus the R square for an independent variable is predicted. Generally speaking, you want them to be above zero point 0.1. That's generally the rule of thumb, more than 10%. And yeah, they're not causing too much of a problem. There are other assumptions which we haven't really got time to go into here with linear regression, but one of the things that can screw stuff up is if I just did if I just went and saved the results here, I can actually ask it to save the unstandardized predicted values here and say, let's look at that and click OK. It reruns the analysis, but it creates a new variable. Here's the predictions. I'm just going to get rid of the decimal places here and just get that done. Say one decimal place. Here's the predictions, the number You can see sometimes it can't predict an outcome because that value is missing. Value is missing, so percent unemployed. But I could do a chart, and that chart would have an R square, which would be equivalent to the model because this is the result of the model. This is what we get. So if I said, here's the mean per capita, I'm going to just hit reset here. Here's my target field. I'm going to do a scatter plot. And here's my prediction, unstandardized prediction. Click OK at that point. And one of the problems that you might get is a funneling. If you get a funneling shape, it can mean that you have what is called heteroskedasticity. You want homoskedasticity. It basically means that the model's less reliable, as you move to the extremes because it's funneling. The error gets greater, and there are various ways in which you can test this and check for it. So I went to linear regression here, and I went to plots. You can do things like let's see, what is it? It's the Z residual, what's called the residual, the standardized residual by the predicted. You can say, give me normality plots and stuff like that. You want these things to be kind of normally distributed. Runs that, runs the whole thing again, gives me some extra output here. Interesting, pretty normally distributed here. This looks quite good. Generally speaking, linear regression doesn't require your dependent variable to be normally distributed, but it does like the residuals. That's the error. Do you remember the residuals? The difference between the points and the lines. It likes them to be normally distributed, likes the error. So if these points fall pretty much perfectly on that straight line, they're kind of normally distributed. And it also gives you this plot here, and it's saying, is that funnel shaped? Well, it's actually not too bad because we can see here that it's not, once you get past the 0 point, it's not funneling too bad. So it's not terribly heteroskedastic. You might get away with that. It's not a massive problem with it, but it's just something you need to be aware of. Okay. So that's linear regression. That's working with linear regression. We've shown you how to do that. You can actually, if you look up some of the other videos we have, you'll be able to see that you can actually save out your model as an object, as a file, like an XML file, and you can apply it to other data sets. You can actually apply it to a new data set, and it will just apply that model and produce predictions for you, assuming they've got the same variables, of course. This leads us to the next examples we've come up to the end here in the last 15 minutes, which is having established what linear regression looks like. How does logistic regression vary from this? So logistic regression allows us to predict things that linear regression can't, such as chance of readmission within 30 days, the risk of sepsis, the likelihood of no-shows to a clinic, the probability of a relapse, staff retention likelihood, or it creates these odds ratios. In the previous session, we were talking about odds ratios and relative risk values. It actually creates odds ratios for you in case control studies. And it helps you model the effects of comorbidities on procedure outcomes. So it's like linear regression, but here the target is a category. Now, because the outcomes are not continuous in nature, standard linear regression won't work because standard linear regression won't understand that there's only two values. It'll predict values outside of those bounds. When the outcome consists of two categories, we use binary logistic regression. And when the outcome has three or more categories, we use multinomial logistic regression. Logistic regression gets around the limitations of describing relationships of straight lines by using a special sigmoid curve. And it looks like this. So this sigmoid curve, linear logistic regression, doesn't use a straight line, uses a sigmoid curve. Generally speaking, within the world of statistics, when they see a phenomenon, what has happened in the past, particularly prior to computing capabilities, is that statisticians have looked around to say, is there a curve that shows that relationship? Well, if you've got a relationship, if you've got a distribution where there's basically only two values, you're trying to model that, and an S-shaped curve kind of talks about it, kind of models two values. There's kind of a situation down here and a situation up here. So if you imagine you have a situation where you're trying to figure out, I don't know, the probability of somebody responding to an offer, and you're offering them a discount. Say you've got a new iPhone that's come out, you're a shop that's got a new iPhone. And if you don't sell that iPhone with any sort of discount, you're not going to sell it because why would anyone buy it? So the probability of responding to the offer is zero, let's say. Why wouldn't you just buy it directly from Apple? If you start to increase a discount and say, well, I'm going to give you a 10% discount, and the probability of people responding to an offer increases until eventually you got, a discount of 100%. And why wouldn't you just go down and get a new iPhone? Even if you didn't want one, you could use it. So it's simply showing that as a value increases or decreases, that it can be related to the probability of a response, probability of something happening, but we shouldn't assume that a straight line is the best way to discriminate between those two conditions. We can use this sigmoid curve, and indeed we can kind of stretch it or squeeze it based on some functions within the routine to help us discriminate better. Obviously, there's a point where it's zero point 0.5. Now, the key here is there is a special formula that converts the values of the predictor coefficients on the x-axis to the values on the predicted probabilities on the y-axis. So that means that, if I was doing if I'm doing linear regression, of course, we can look at the relationship directly through a scatter plot. And I can say for every 1 unit change in the median value of income, median decile of income, it has this effect upon the dependent variable. You can't do that with logistic regression because it's not a straight line. It's based upon the sigmoid. So a 1 unit change doesn't have the same effect. So that means you're going to have to do something to the numbers to make them to convert them in some way so that they can spit out a probability at the other end. And at this point, we're saying, well, what are these numbers on the x-axis? Well, these are the coefficients that the logistic regression creates for us. And they cannot be directly interpreted in the same way that the linear regression can be shown. And they are, in fact, based on the log of the odds. So it's bad enough to think in terms of the odds of being, rather than even the probability, but the odds of, say, in this case, having a low birth weight baby. But it's not even that, it's the log of the odds. And the reason why it's the log of the odds is because it's simply because these numbers can be converted via a little formula called a link function, which spits out probabilities at the far end. So the downside is that they can't directly interpret them in the same way that you can linear regression. But the upside is that you get a better model out the back of it. You can also get odds ratios, which we'll see in a moment, and it gives you a probability value. Okay, so we want to use the logistic regression to model low birth weight. How do we do that? Let's have a look at the data set. We're going to open up a data set here. Let's see, where is it? It's birth weight. This is quite a famous data set. How many cases are in it? Let's see. 378. Okay. Let's just look at our target field here, which is simply labeled low. 68% had normal weight. Oh, these mothers had normal weight, and 31% had low birth weight. Okay. Um, let's look at something. Let's look at a really simple variable here. We've got various variables. We've got age. We've got the weight of the mother at last menstrual cycle. We've got their ethnicity. Here it's labeled race. We've got whether or not they smoke. We've got history of premature labor, which is actually a binary field. Shows it here as a continuous field, but it's actually just none. We've got history of hypertension, and we've got presence of uterine irritability, and we've got number of physician visits during first trimester, and we've got the birth weight of the baby itself. So that's just used to calculate normal birth weight. And obviously there's a cutoff point, an arbitrary cutoff point where they said that's normal, and if it's below that point, it's not normal. So if we go to analyze, we're down to regression now, and we're in the binary logistic because this is binary logistic. This is a binary outcome. And we put low birth weight in here, dependent variable. And this time they're not called independent, they're called covariates. And I'm just going to pick up smoking status, and I'm going to put that in. Now, technically, this is a category field, it's a categorical field. You should tell it's categorical, but in reality, it's just coded as 0 and 1. And amazingly, if it's just coded as 0 and 1, it will treat it as if it's a continuous field, and the results should be the same. Okay, so a value of 1 means that they smoke. And here, a value of 1 means that you have a low birth weight. Okay, so let's see if I run this, what's going to happen? What kind of output I get? Well, this time the output's quite different. It starts off with what's called a classification table. And the classification table simply says, okay, um, assuming we're not using any variables in the model, I'm just going to predict everybody to be normal weight. Why would you do that? Well, because that's the majority group. You might as well just do that. That's 68%. If I did that, I'd be accurate nearly 70% of the time, 68.8%, 69%, you know? So it's kind of logical in that sense. It's kind of your baseline you're kind of comparing against. Then it says, okay, we're going to introduce this variable into the equation. And the variable it's introducing is simply a constant because it's a constant just the way linear regression is a constant. There's a formula that goes with logistic regression and it has a constant as well. And the constant is going to be equal to basically this value here, which is simply saying I'm going to assume everybody's normal birth weight, and that's going to get me, that's better than just assuming it's 50-50. And does that help me predict? Yes, it does. You're likely to be accurate about 69% of the time if you just assume that. If you just assume that, that's better than being 50-50 accurate. And it says variables that are not in the equation at this point is smoking status during pregnancy. And there's a score associated with it. And then we get model coefficients, and we get model coefficients, which are telling us whether or not this variable is statistically significant at that step, at that block, and at that model. Why is that? Well, because just like with linear regression, you can have a stepped entry. And with linear regression, you can actually enter blocks of variables. You can actually say, I want to force these three in, and then I want to have a bunch of variables which are going to go in as using forward a method or a backward method or something like that, where it can choose from them. But I want to force three of them. Why would you do that? Well, because you might be using certain factors which you know from previous studies to have an effect, and you want to make sure they're in the model, so you can force them in. And then the model itself, because you have multiple models. So here the values are the same because everything just goes in one go. That's all it's saying. And then we get an accuracy measure. Now, unfortunately, there aren't nice measures like R-square value here. So it has these pseudo R-squares, and they're always quite low. But suffice to say, the larger the value, the more accurate the number here. So the pseudo R-squares here, Cox and Snell and Nagelkerke, 0.036, not very high values, 0.025. They're just pseudo R-squares. Larger values mean a better fit. The value which is actually used when you're comparing one model to the next is a -2 log likelihood, which you can't really interpret directly because it's literally -2 times the log likelihood. It is literally that abstract. But suffice to say that the smaller the number, the better the fit. So if you wanted to compare one model to the next in terms of the fit, you'd look at the -2 log likelihood, and whichever one had a smaller value, the better. And then we get our classification table after we've entered our variable. And the classification table is still 68.8%. So it hasn't done anything. It hasn't changed the predictions, but that's not terribly surprising. We wouldn't necessarily expect that because in order for it to predict somebody to be low birth weight, it would have to find a case based on smoking, or because somebody was smoking, they had a greater than 50% chance of being low birth weight. So that's the only. So it's just simply telling us that smoking doesn't increase the likelihood of you having a birth weight child on its own by more than 50%. So we don't really care too much about that at this stage. And it's pretty arbitrary. You can see the cutoff value here is 0.5, that's 50%. And then finally, it gets down to variables in the equation, smoking status during pregnancy. And it gives us a value of 0.704. And as I say, unfortunately, this value cannot be interpreted directly. Okay, we can't interpret it directly because it's actually the log of the odds of that effect. The constant is a minus number, but what we can say is it's a positive number, and we can say that smoking status increases the likelihood of a positive outcome. The positive outcome here being that they will have a low birth weight baby. And helpfully, we know it's statistically significant. And helpfully, we have this value here called XB. That means exponentiated B. That is that value raised to the power of E, or the exponent. And this is, in fact, log odds ratio. So it's saying that if you smoke during pregnancy, the odds of the baby having being low birth weight are increased by a factor of 2. So you double the odds. If that was equal to 1, then we would expect that to be non-significant because it doesn't really make a difference. Or if it's a binary field like that, if it's equal to 1, just mean it makes no difference. It doesn't increase or decrease. If it reduced the odds, then that value would be less than 1 because it would be reducing the odds. And this value here would be negative in nature. So we could actually take this value here and we could put it through what's called a link function. The formula is 1 over 1 plus e to the power of minus z, and that punches out a probability value for you. It shows you the probability that that person a is in fact likely to be low birth weight. In fact, let's do it now. Let's just run it. Let's go save. Just save the probabilities and go continue and click OK at that point. And let's find somebody who smokes. There's people who smoke here. Look, that's the probability. 0.4. And look, these are people who don't smoke. 0.25. So that's the effect of that. It's not greater than 0.5. It's not greater than 0.5. So it's still more likely to be healthy birth weight than low birth weight, but it's getting close to that. So there you go, hit that. So that's what that formula produces for us. So we can see the effect of that. So let's just go back, switch that off. Okay, let's put in the other variables now. At this stage, I'm actually going to enter the variable race. And I'm going to tell it the race is in fact categorical. This is ethnicity, of course. There are 3 values here. It's not binary anymore. So now I need to tell it this is a category field. And this is where we create what are called contrasts. And contrasts basically mean I'm going to choose one of these categories and I'm going to create 2 pseudo variables from it. And these pseudo variables are going to be in relation to that category. Now, by default, it just chooses the first one. You could choose the last one. The first one happens to be white people, and then we have black people or other. Okay, so if I throw that in, click OK and run that. Now we've got same as before, but look, let's go down to the bottom here, and it says race 1 and race 2. Okay, what does that mean? It means that the coefficient, it says the effect of not being white, basically. In this case, it's be black and other. So this one refers to black or white or other or white. That's basically what it means. So it's called dummy coding, and it takes them as contrast. So it's saying, look, in fact, the exponential b now says that in the presence of these other variables, holding white people as sort of constant, the odds actually increase close to 3 in this case. So the odds so this is a very significant value. This is how we can make sense of this. We can say the effect of being black rather than white increases the odds in the presence of the variable smoking, increases the odds by a factor of close to 3. And the presence of being other than white increases the odds by a factor of 3. This is based on, I think, US data. Now I can throw in these other variables like history of premature labor, birth weight of mother, I can put history of uterine irritability, hypertension. I can put these other variables in weight of mother, age of mother, and ask it to choose a method like forward likelihood, which is a forward method, and ask it to start adding in the most important variables one at a time and stopping when it can find no more significant variables to contribute to it. So the final model, as we can see, it says beginning block 0. Here's all the 0. Here are the variables that are not in the equation at this stage. And then it says, okay, step 1, step 2. So it actually just chooses, it looks like it's just choosing 2 variables. It chooses, oh, sorry, beg your pardon. I put in the wrong one. I put in the weight of the birth weight in grams, which of course is actually what the variables, dependent variables based on. So we can't have that. So we put that in again. Okay, run that again. Okay, and then we end up with a model which has 6 variables in it. We can see at each stage the -2 log likelihood gets smaller and smaller and smaller, and we can see the R square is getting larger and larger because, of course, as we're adding more variables into it, we get more predictive accuracy. And we can see the classification table there then by step 6 is predicting 91% of the normal birth weights accurately and 35.6% of the low birth weights accurately. If I change the cutoff value here, let me just play around with this and show you the effect of this. I've got options here. I'm going to change the cutoff value here and say, look, I'm just going to make this 0.45. Just changing it from 50% to 45%. It won't change anything else. But look, now I'm predicting where's my table here? 37% of the low birth weights are accurately predicted now, nearly 40%, because I've changed the cutoff value to 0.45, 45%. If you're above 45%, I'm going to predict you to be a low birth weight. If you're 45% risk rather than 50% risk, so I can play around with that. And then it comes down to variables in the equation. At step 6, this is what we end up with. We end up with smoking status. We ended up with the variable race. We end up with history of premature labor. We ended up presence of uterine irritability, history of hypertension, and weight of moderate last menstrual period. And we can see that everything apart from weight of moderate last mental period is positive. So everything has a positive correlation with having a low birth weight baby. If I just stretch this out a little bit, and you can see that they're all statistically significant. Some of them are getting very close to non-significant here. The constant isn't significant, but that's kind of what you expect. It's the weakest part of the equation. It's a little bit on the end. And you know, that's the model we end up with. And it gives us information on the variables that didn't end up in the equation because they weren't statistically significant at that stage. If I wanted to show you the results of that, let me just make sure I'm closing this down. Maybe go pivot table. I've got this pivot table up in the background here. Just close it. If I want to show the results of that, I go logistic regression and say, save out the probabilities for me and save your predicted group membership. Click continue and OK. And this is the probability, and this is the predicted group membership. Let's just do a quick chart. And I'll say I'm going to ask for a box plot here, which is a way to compare two a group next to each other. So this is the I'm going to say here's the predicted group. This is the predicted group, and this is the probability. There. And what you'll see is that look, there's clear blue water here. It's saying that once you're above 0.5, I'm going to predict you to be low birth weight. And once you're below 0.5, I'm going to predict you to be normal birth weight because the 0.5, this is the probability of having a low birth weight baby. And this is based on its predicted groups. How does that map to the actual groups? Well, if I run it again and swap out the low birth weight actual group, then now we expect there to be error. We expect there to be an overlap. And sure enough, there is an overlap, you know, we expect, because this is the actual. But we can see that, of course, those of low birth weight, you know, tend to have higher probabilities of having a low birth weight than those of normal weight. There are some extreme. There's some normal outweight people here who have actually quite high probabilities. The outliers extreme of being predicted to be of low birth weight. But that is a way for us to kind of start playing around and examining the model itself. Okay, that brings us to the end of that session. Just be aware that IBM Statistics has a lot of regression methods, and the regression module adds several key methods like logistic regression to the standard methods are available, and many other methods are available through SPSS's integration of R and Python. There are some links to additional resources here about regression and about significance tests and that sort of stuff, so you might want to look at that. And you should be aware that we provide a portfolio of online training materials which are free to our existing customers or available for purchase. We have a number of different consultancy services that we provide, including side-by-side consultancy, hand-holding, training consultancy, classroom training, but we offer no strings attached technical business advice to all comers. Do hope you found that useful and look forward to you logging again at some point in the future. Thanks very much.